Hello, algebra students. It's Mrs. Ailstack here. This video covers Module 04.02, Operations with Radicals. Before we get started, please make sure that you have both a writing utensil and paper, so that way as you watch the video, you can pause it whenever you need to, take notes, and complete the examples alongside me. We're going to try to make this as close to being in class as possible. Before we dive into operations with radicals, one of the pieces that we need to make sure we all understand is where radicals fall within the real number system. So the real number system is something that was covered in 8th grade in pre-algebra. So hopefully as I review this, the pieces will kind of start to come back to you. In the real number system, it's broken up into two pieces. On the left here, we have our rational numbers. And on the right, we have our irrational numbers. So rational numbers, as you can see by the graphic organizer, is broken up into different subgroups, into different smaller pieces. The very first rational number that we're going to discuss are natural numbers. These are sometimes referred to as your counting numbers. So it's what you would have learned as a toddler when you were first learning to count, your counting numbers. So like 1, 2, 3, even larger numbers like 10, 50, 100, etc. All of those numbers from 1 and above, if we kind of visualize a number line, are considered our natural numbers. Then our whole numbers. If you look here, the natural number box is inside of the whole numbers. That's because your whole numbers include the natural numbers, but they also add, oh no, I lost my mouse. There it is. All right, so the natural numbers also include the value of 0. So whole numbers include 0 and all of the natural numbers. That's a number sign, not a hashtag. Technically, it's a pound sign. That's what it was called first, and then you guys changed it to hashtag. All right, with our integers, similar to above, that the natural numbers and whole numbers are included within that. So our integers are all of our whole numbers and natural numbers, but they also include the negative values. So like -50, -10, -1, and all of the whole numbers. And by me saying all of the whole numbers, that does include the natural numbers as well. So this is why a lot of the times you've probably heard me or Mr. Masonoff or Mr. Lasanti refer to our numbers as integers, because that includes negative, whole, and natural. So all your positives and negatives. Now all of these numbers are considered a rational number. But there are numbers that are rational that don't fit within the integer, whole, or natural category. And that would be fractions, some decimals, and some radicals. So first, all fractions are, or a majority of the fractions are considered a rational number. So let's use the fraction 1/2 as an example. 1/2 is a rational number. One of the reasons that 1/2 is rational is by converting it to a decimal. What would 1/2 be as a decimal? Hopefully, you said 0 and 5/10. 0 and 5/10 is a decimal that terminates. It stops, right? It has a rational, it has a specific value. So any decimal that is a terminating decimal, has a stopping point, is classified as a rational number. The other kind of decimal that's a rational number are repeating decimals, ones that repeat the same value forever and ever. For example, 1/3. As a decimal, 1/3 can be converted to 0 And I'm just going to write it as 33 hundredths, but it doesn't really stop there. It's repeated. It's 3, 3, 3, 3, 3 forever and ever and ever, to infinity and beyond. So those are the two forms of decimals that are rational numbers. Ones that terminate, like 0 and 5/10, and ones that repeat, like 1/3 as a decimal, 0 and 3 repeating. Now let's get into radicals, because that is one of the main focuses. Some radicals are rational numbers. For example, if we have the square root of 36, what is the square root of 36 when you simplify it? Well, it's a perfect square because 6 times 6 is 36. So the square root of 36 is 6. Now, 6 classifies as an integer, a whole number, and a natural number. So because when you simplify the square root of 36, you get an integer, you get a whole number, okay? That is why the square root of 36 would be considered rational, because when simplified, you get a whole number. Your radical goes away, you have a rational value. All right, let's jump over to irrational numbers. So irrational numbers are decimals that don't fit in to the two categories we discussed. So they never stop and they never repeat. One of the most famous examples for an irrational number is pi. Pi Day was actually the very first Saturday of your guys' spring break, 3.14, March 14th. Well, Pi Day, when we approximate its value, we often refer to it as 3 and 14 hundredths. But that decimal does continue. That's just where we choose to truncate it, where we choose to stop it. But it really continues forever and ever. So it never terminates and it also never repeats. So that's what my ellipses, my 3 dots here means, is it keeps going forever. Now, as a radical, a lot of our radicals are going to be irrational numbers because we don't have very many perfect squares. So if it's the square root or even the cube root of something that is not a perfect square or not a perfect cube, it's going to be irrational. The square root of 2. When I approximate the square root of 2, and you guys can even put it in your calculator to verify, or the calculator on your phone, when we have the square root of 2, it is approximated to be 1 and 4, 1, 4, 2, and it keeps going. Now, of course, it has to stop on your decimal, but stop on your calculator, but that's because your calculator runs out of room, so that's where it's truncating it, that's where it's stopping it. But it really continues. And it kind of looks like it might repeat because it goes 4, 1, 4, but then we have a 2, so it's not a repeating decimal. So irrational numbers are your non-perfect squares, and the reason behind that is if you take a non-perfect square and you convert it to a decimal, it never terminates and never repeats. So one other example would be like the square root of 7. 7 is a prime number. It's not a perfect square. I can't simplify it. So when I convert that to a decimal, I have 2 and, what happened to that 6? 6, 4, 5, 7. Repeat, and it does not repeat, but it continues forever. All right, so to summarize, real numbers are rational and irrational. Within the rational category, that's all of your integers, so positive and negative numbers, fractions, decimals that terminate, decimals that repeat forever, and perfect squares. Your irrational numbers are numbers of their values that are, when converted to a decimal, they never terminate and they never repeat. So that does mean there are also some fractions that could be considered this as well. All right, let's move forward and talk about simplifying radicals. So before we can move into operations with radicals, we need to know how to simplify them. So for this first example, and just as an FYI, there are a total of 8 examples for those of you spacing things out. We're going to simplify using the method of prime factorization. Now, prime factorization was something that you guys would have learned in elementary school. And a lot of times, the method of organization is to create a factor tree. All right. So hopefully, as I use prime factorization in a factor tree, that stuff will start to come back to you guys. All right. So if we look at the square root of 80 here, the square root of 80, I can't just simplify it and get a rational number because it's not a perfect square. The closest perfect square would be 81. The square root of 81 is 9. Well, that's too big. 81 is bigger than 80. So if I go down, well, 9, then 8. 8 times 8 is 64. 80 falls in between there. So 80 is not a perfect square. Therefore, the method for simplifying is to break down and do the prime factorization. All right, so with 80, all right, we are struggling with my mouse. All right, why it says it's on draw. Why is that not working? All right, let's try this. There we go. Okay, so I'm on example 2. Dagnabbit. Well, I'm just creating some humor for you guys, apparently. All right, so clear the drawings. Let's draw. All right, 80. So we need to break 80. The prime factorization means I'm going to break it down until it's all primes. So 80 is an even number, which means it's divisible by 2. So 2 times 40 is 80. All right, well, 2 is a prime number, so that branch of my factor tree stops. But 40 is not prime, so I'm going to continue to break that down. So here's our next branch in our tree. So 40 can be rewritten as 2 times 20. Right, 2 is prime, so that branch stops, but 20 is not. So 20 is 2 times 10. All right, 10 is still not prime, so I got to keep going. 10 is 2 times 5. Ah, looky there. Now I have all of my primes. So I personally like to circle my prime numbers because that helps them stand out, because we only want to look at our prime factorization. I don't want to look at my composite numbers, so my 10, my 20, and my 40. One way that you guys can double check that you did the prime factorization correctly is to just quickly do the multiplication. So whether it's in your head, whether it's on a calculator, if you take 2 times 2 times 2 times 2 times 5, you get 80. So it's a quick way to make sure you did your prime factorization correct. All right. The reason that we break this down into prime factorization is we have the square root of 80. So I am looking to simplify by seeing if there's any hidden perfect squares within the 80. Now, to know if something's a perfect square, a little rhyming trick that I use is we look for pairs that turn into squares. So right here, I have a pair of 2's. Would you agree that I could rewrite 2 times 2 as 2 squared? Yeah. And then what is 2 squared? Well, 2 squared is 4. And then we just said that we're taking the square root. See, we have the square root of 80. So the square root of 4 is 2. So the reason for all that kind of little logic train there is to say that if you find a pair of numbers, so 2 of the same number, that means it's really a perfect square because 2 times 2 is 4 and the square root of 4 is 2. All right, so we need to find out if we have any other pairs of prime numbers. We do. We got another pair of 2's. So again, same thing. That is really a perfect square because 2 times 2 is 4. And then we're left with this lonely 5. Does the 5 have a pair? Nope. So that means the 5 is prime. The 5 doesn't have a pair, so it's not a hidden perfect square. Therefore, he's going to be left inside. He can't get out. Now, if we look back, now that we've identified our pairs, now we can do the real simplification. So here, we have our first pair of 2. 2 times 2 is 4. The square root of 4 is 2, which means 2 is outside of your radical. And then I had another pair of 2's. 2 times 2 is 4. The square root of 4 is 2. So another 2 comes outside of your radical because they were perfect squares. But your 5 doesn't have a pair. He's not a perfect square, so he has to stay inside. And in case some of you need that, this 2 came here, this pair of 2's is here, and this 5 is here. Now, this is really close to being done, but we want a fully simplified answer, which means I need to complete the multiplication outside of the radical. So 2 times 2 is 4. So 4 square root of 5 is the radical, or is the simplified radical of the square root of 80. So just to kind of prove to you that these are equivalent, if I put them both in my calculator, the square root of 80 and then the simplified answer that we got, 4 times the square root of 5, we have the same decimal. So these are equivalent forms. They're equal. It's just 4 square root of 5 is the simplified version. Just like 1/2 and 2/4 are the same thing. They're equivalent. One is simplified, one is not. All right, let's hope I can get to my mouse and go to the next slide. All right, let's try that again. Now, if example number 1 made sense to you, I encourage you all to pause the video and try number 2 on your own and see if your work matches mine. If it didn't, you'll get plenty of time to practice later on, so please just keep following along and taking good notes. All right, we need to simplify 5 times the square root of 28. Well, I always want to see if it's a perfect square. Nope, 28 isn't because 4 times 4 is 16, 5 times 5 is 25, 6 times 6 is 36. Nope, it doesn't fit into that. So the way that I can simplify is by doing my factor tree, breaking down my 28 into all of its primes. So 28 is an even number again, which means it's really nice because I can start with 2's. So 2 times 14 is 28. 2 is prime, so that stops. 14 breaks down and can be rewritten as 2 times 7. Oh, look, both of those are primes. So that was a quick one. I am already done with my prime factorization. All right, what we're looking for here is our hidden squares are pairs. We're looking for pairs that turn into squares. So I have a pair of 2's. So that is a perfect square, which means it's going to come outside of our radical. All right, if we look at our original problem, we have a 5 being multiplied on the outside. So I cannot forget about that 5. And then we had a pair of 2's. So we can take the square root, so it comes outside of the radical. So we have 5 times 2. And then our 7 did not have a pair, and it's not a perfect square, so it has to stay inside of the radical. So that's where we got the 5 from, the 2, and the 7. Now we're almost done. So what do you guys think we need to do next to finish simplifying this? Hopefully you said multiply 5 times 2. And if so, you were correct. 5 times 2 is 10. 10 times the square root of 7. And that is our simplified and final answer. Now, 10 times the square root of 7. Is that an example of a rational number or an irrational number? It's an irrational number because the square root of 7 is not a rational number. The square root of 7 as a decimal is one that never repeats, it never terminates. Therefore, this is a rational number. Okay. All right, now, hopefully that made sense to you guys. Please remember that since this is a video, you can pause, you can rewind, but just know that if it's still a little fuzzy, we're going to get lots of practice as we do our operations, so you'll have more of a chance to practice this on your own. All right, 3 and 4. Better clear this. All right, so the operations we're going to start with is adding and subtracting our radicals. So if we look at example 3, it's asking us to simplify, and I have negative 10 times the square root of 7 plus 12 times the square root of 7. What I want to relate this to is way back in 6th grade, I think, when you started learning about combining like terms and we started having variables. It's very similar to that. So if I just create a random problem over here to relate it to, let's say you had negative 10x plus 12x. Well, are they like terms? Yeah, they're like terms because they both have the variable x. So that's what we're looking for in radicals. When we're adding and subtracting, they need to be like terms. So instead of having the same variable, they need to have the same radical. So here we have the square root of 7 and the square root of 7. So these are like terms because they both have the same radical. Therefore, I can combine them. I can add them. Now, I only add the negative 10 and the 12 because again, just like when we did variables, when you're adding, it doesn't become an x squared. It's just you have negative 10 x's, so you owe somebody $10, but then you pay them back $12. So you were nice, you paid them interest, or maybe you weren't nice and they just charged you interest. Okay? Oh, same would be here. Because they both have the square root of 7, they're like terms, so I'm able to add them, but I focus on adding that coefficient. So negative 10 plus 12 is 2 square root times the square root of 7. Right now 7, because I want to think if I can simplify it like I did on example 1 and 2, but nope, 7's a prime number, so that is the simplified answer. That's it. 2 times the square root of 7. And is this a rational or irrational number? It is irrational because we still have the square root of 7. So that is an irrational number. All right, number 4. So here we have a lot more terms. Okay. So let's take a moment and explain, just like we did with variables on number 3, what this would look like if it was written with variables instead of radicals. It'd be like 4x plus y minus 3x plus 6y. So we're looking to combine things, we're looking to add our like terms. So sometimes you have more than one variable, same here for example 4. Sometimes you have different types of radicals. go back to our original problem now. So 4 times the square root of 11. Are there any other like terms? So are there any other terms that are also the square root of 11? Yes, this one right here. When you identify this, please make sure you take the sign with you because that tells you whether you're adding or subtracting, which is key. So that minus sign in front of the 3 belongs to the 3. So we have 4 times the square root of 11 minus 3 times the square root of 11. Well, that would be 1 times the square root of 11. Just like with variables, we have those invisible numbers. Remember, mathematicians are lazy. They have invisible numbers all over the place. So we don't need to write that 1 because the square root of 11, since one of them is there, that goes ahead and is enough. It tells me that I have only one of them. All right, do I have any other like terms? Hopefully you noticed that we have a square root of 5. Oops, I keep clicking on the wrong thing. And then another one, another term with the square root of 5. Oh, when I go to combine these, what do I get? Hopefully you remembered that invisible number thing, because if I have the square root of 5 here, that means I have one of them. So there's really an invisible 1. So get rid of that invisible ink if you need to. Put a 1 there in your notepad. So 1 plus 6 is 7. All right. Am I finished, or can I simplify it further? I am finished. This is the simplified answer because I don't have any more like terms. And if I look at my radicals, the square root of 11, that's a prime number and it's not a perfect square. Same with 5, prime number, not a perfect square. So there is no further simplification that I can do. And this would be another example of an irrational number because they both, if I convert them to decimals, would not terminate and they would not repeat. All right, we have one more example here for adding and subtracting. So we want to simplify 2 times the square root of 6 minus 2 times the square root of 24. They don't look like terms to me because they don't have the same radical. So when that happens, we need to think back to example 1 and 2, and we need to see if maybe we can simplify our radical, and then maybe some hidden like terms will appear. So we focus on our 6. So we have 2 times the square root of 6. 6 is not a perfect square, and it's also not a prime number. So if we do the prime factorization for 6, we have 2 times 3. Oh, well, 2 is prime and 3 is prime, so I'm done. But 2 and 3 are not the same number, so they're not a pair, which means I can't simplify that any further. So the 2 times the square root of 6 is going to have to stay the way it is. All right, so let's try the 24 then. Because 24 is not a perfect square and it's not prime, but it is an even number, which means I can start by dividing it by 2. So 2 times 12. And I encourage you guys to pause and try to do the prime factorization of this yourself. All right, 12 can be rewritten as 2 times 6. 6 is 2 times 3. All right, I have all of my primes. So once again, for organization's sake and to help keep me from making a copying error, I want to circle my prime numbers so they stand out because those are the only numbers I'm looking at for pairs that can turn into squares. So 2 times 2 times 2 times 3 is equal to 24. So it's the prime factorization. All right, let's see. 2 times 2, so I got a pair of numbers here. But then I have another 2, don't have a match for him. I got a 3, and I don't have a match for that guy. All right. Well, when we write this, please, please, please don't forget about your coefficient. Don't forget about this tag along right here. That is in front of the square root of 24, so he's coming along for the ride. He's that annoying little sibling that just keeps following you around and won't leave you alone. We have to bring him down. Mom and Dad say we have to babysit, so we got to bring him. So -2 times, and then now if we look at our primes, we had a pair of 2's, so that's a perfect square. So we have our 2, and then we have a 2 and 3 left on the inside because they did not have any pairs, so they're not perfect squares. All right, what can I do to simplify this further? Hopefully you said multiplication. So -2 times 2 is -4, and inside your radical, 2 times 3 is 6. Looky there. If we look back at our original problem, we had a square root of 6. So now that we simplified it, we do have like terms. So we can simplify this expression. So we're gonna bring, oopsies. I'm gonna bring this guy down. So what we're working with now, just to try to make it clear, is 2 times the square root of 6 minus 4 times the square root of 6. 2 minus 4 is -2, and then your square root of 6's, because we're just saying how many of them we have, we're just combining like terms, that stays the same. There we go. We have a simplified answer that is an irrational number. All right, awesome job, guys. All right, before we move on to multiplication, I have a weird fact of the day for you. Oh, did you know that Coca-Cola would be green if the coloring weren't added to it? So it'd be kind of more like Mountain Dew, I guess. Or that kind of looks like it's a cup of tea, like matcha green tea. But yeah, so there you go. Coca-Cola is brown in color because of food coloring. All right, let's get to multiplication. And this is the last segment of our video. So we have 3 more examples left, guys. You're doing good. All right, now with multiplication, our rules are a little different than with adding and subtracting. So we need to simplify 3 times the square root of 12 times the square root of 6. Oh, when you multiply, remember you can multiply unlike terms. So if we go to our variables, uh-oh, what happened? There we go. As our example again, so if we had 3 times x, well, could I take 3 times x and just rewrite it as 3x? Yeah, because 3 and x aren't necessarily like terms, but when you multiply them, you can write them together. You can combine them. So, same thing with these. My property, one of my rules, is that if I am multiplying with radicals, I can rewrite them under one radical. So we can rewrite this as 3 times the square root of 12 times 6. I want to do a little check in my head here before I move forward. What is 12 times 6? Well, 12 times 6 is 72. Now, is 72 a perfect square? Nope. So, I actually am going to keep it then as 12 times 6. Because when I do my prime factorization, we're breaking apart our numbers, right? Well, if I change it to a 72, that's a lot more work, and that's a lot harder number to do in our head, where 12 and 6, those are small numbers. You can probably whip out that prime factorization like that. So It's always good to check and see if you get a perfect square, but if you don't, as a time saver, I encourage you to leave your numbers separate, and that'll save you a little bit of time and a little bit of work when doing your prime factorization. You don't have to do that, but it's what I'm going to do, and it's just a little tidbit. All right, 12 for our prime factorization is 2 times 6. 6 is 2 times 3. All right, got all of our primes here, but I'm not going to circle them yet because 12 and 6 are under the same radical, so I want to circle all of my primes. So 6 is 2 and 3. All right, now this is where it could get a little bit messy, so I am going to circle them. But after I circle them, I'm going to choose to be organized and rewrite them. So all of our primes are right here. And again, a good thing is you could multiply those together real quick and you should get a 72. And that would tell you that you picked all of your primes and you did it correctly. So I'm going to rewrite that just so I don't make any errors. So I'm going to put all of the 2's together. So we have 3 2's. So check, check, check. And I have 2 3's. Check and check. Didn't leave anybody behind. Now it's a little bit more linear. It's a little bit more organized. So we need to look for our pairs because they're really hidden perfect squares. We have a pair of 2's. That's good. Oh, this guy's lonely. Doesn't have anybody. Oh, we got a pair of 3's. That's it. All right, so your pairs can come outside of the radical. They're perfect squares. We've taken the square root of them. So we have our tag-along sibling here. We have our 3. And we have a pair of 2's. So 1, 2 comes out. This guy's going to have to stay inside. And then we have a pair of 3's. They can come outside. All right, what do we need to do? What's our last step? Yep, multiply. So 3 times 2 times 3. 3 times 2 is 6. 6 times 3 is 18. So 18 times the square root of 2. That is our final and simplified answer. And is that rational or irrational? Yep, it's an irrational number. And if you're ever unsure, plug it into your calculator. And if it's a decimal that keeps going on forever and does not repeat, it is an irrational number. All right, numero 7. Is that number 7? All right, this one right here is very similar to number 6. So I would encourage everyone to pause the video, try number 7 on your own, and then you can hit play and compare your work to mine. So fingers crossed you'll get it correct, but if not, that's what learning's all about, is making mistakes, comparing, so then you can get it right and figure it out in the long run. Every time I do this, my mouse goes away temporarily. Come on. All right. Oh. One of my properties is when it's multiplication, I can combine the problem underneath one radical. So 18 and 3 and 4 is on the inside. Y. There we go. Okay. All right, well, 18 times 3, let's see, that is 54. Nope, 54 is not a perfect square, so I don't really want to multiply. Let's make our life easier and just break down the smaller numbers. So 18 for its prime factorization, it is an even number, so I can divide by 2, 2 and 9, and then 9 is 3 and 3. All right, and then this 3 up here, well, that's already prime, isn't it? So I just have to make sure I include him when I circle my work. So this is where it's your choice. If you guys are able to see those numbers, you don't have to rewrite it. But if that just looks really messy, please take the extra second and rewrite it. If that's what it takes to get it correct, then do it. All right? Now, what are we looking for? We're looking for pairs because pairs turn into squares. So right here, I see a pair of 3s. This 2 is lonely, he doesn't have a partner. This 3 is lonely, neither does he. All right, let's rewrite it. So we have our 4 out front. We can't forget about him. He's the annoying sibling. He's going to make sure you remember. We had a pair of 3s. So that is the square root, so that can come outside. This 2 didn't have a pair. He's left on the inside, as is the 3. All right, we're almost done. 4 times 3 is 12. On the inside of a radical, 2 times 3 is 6. So here we have our simplified answer, 12 times the square root of 6, and that is an example of an irrational number. All right, you guys are doing good. We just have one more example. All right, I think I got my cursor here. All right, so we need to simplify the square root of 3 times the quantity of 5 plus the square root of 3. Does this look familiar to anyone? Okay, if it does, great. If not, what if I gave you this problem? What if we had 3, or actually let's make that in, yeah, we'll make it 3x times 5, no, just x, keep changing my mind, x times 5 plus x. Hopefully this is where you'd say, well, we can't follow order, well, we can follow order of operations, but my parentheses, my grouping symbol, 5 and x aren't like terms, so I can't combine them. So what's that trick? The distributive property. So we can distribute, just changed colors there. So we can distribute, and that will clear our parentheses. So we have the square root of 3 times 5. All right, when we go and do this multiplication, is our 5 inside of a radical? No, it is a whole number. So we just need to have 5 in front, 5 times the square root of 3. Just like over here, we would have 5 in front and then just times an x. That's what we're going to have when we do this multiplication. Just 5 in front times the square root of 3. Because the square root of 3 is kind of like a variable where you can't do 5 times 3 and get 15. They're two different things, so we just have to show them as being multiplied since I can't physically multiply them right now. All right, with the distributive property, you have to multiply what's on the outside by everything on the inside. So the square root of 3 is also being multiplied by this positive square root of 3. All those rules that we just did said if we multiply radicals, we can combine the information under one radical. So plus the square root of 3, this guy right here, times the square root of 3. All right, well, what is 3 times 3? Well, 3 times 3 is 9. Hey, is that a perfect square? It is. And right here is kind of nice visual proof on why pairs are perfect squares, because the square root of 9 is 3. And didn't we have a pair of 3s? Okay. So if you notice it's a perfect square, don't break it down into the primes. You got your answer. All right, let's bring this bad boy down. So 5 times the square root of 3 plus 3. All right, are we done, or can we simplify this further? Yep, we're done because we don't have any like terms that we can add. The square root of 3 is already simplified. So this is our final answer. Now, our answer as a whole is considered an irrational number. But if we wanted to specifically look at our 3 here, oops, I should have changed the color. If we want to specifically look at our 3 here, that 3 itself is a rational number because the square root of 9 is a perfect square, so that square root disappeared, which made it a 3, and a 3 is a rational number. All right. Thank you guys for taking the time to watch this. I really hope it helped. But as always, we really are here for you. We want to assist you, whether it be answering an easy question on email or text, or whether it be having an individual lesson to go over something that is difficult for you, or a small group lesson on Zoom or a phone call. We are here for you. Please just reach out and let us know. All right, good luck as you guys take your 04.02 quiz. Bye.